You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. James M. Jackson. Dr. Jackson is an astrophysicist and the director of the Green Bank Observatory. Before joining the GBT, Dr. Jackson has served as Associate Director for Research for the Stratospheric Observatory for Infrared Astronomy with the university's Space Research Association. He has also led administration and research in astronomy and astrophysics for the University of Newcastle in Australia and Boston University, and served as Assistant Director for the Centre for Astrophysical Research in Antarctica. He has co-authored 148 journal articles with over 12,000 total citations.
For a more in-depth look at the realities of exploring our galaxy and the universe at large, I recommend starting a free trial for the course Astrophysics over at brilliant.org. There you will learn in depth, through interactive exercises, how to calculate and determine the habitability zones around stars where Earth-like planets suitable for human colonization might lie, and exercise and improve your math skills in the process. I found it to be a great resource for learning how astronomers discover exoplanets in the first place by exploring the transit method and looking for the gravitational wobbles planets produce on their parent stars. And finally, an interactive exercise covering the basics of interstellar travel, which will really help you get a better feel for the realities of exploring and colonizing the Milky Way. Utilizing fun, interactive exercises can help anyone better understand this universe in which we live. Brilliant provides courses for all ability and knowledge levels. Use my link and get started with Brilliant for free. And the first 200 people will get 20% off their annual premium subscription. So go and click the link below or go to brilliant.org/Event Horizon. Dr. Jim Jackson, welcome to the program.
Oh, thank you so much for having me. Delighted to be here.
Now, Doctor, you recently became the director of the Green Bank Observatory, the venerable Green Bank radio telescopes, both of them. And I've actually followed that observatory long enough to remember the collapse of the original telescope.
Oh, gosh.
And the rebuilding of an even bigger and better one. Now, how long have you worked, before becoming director, how long have you worked with this observatory? So
I was a client. So for my first 25 years of my career, I was at Boston University as a faculty member there. And I'm a radio astronomer by trade, and I guess it's also a nice hobby of mine. So I've been using Green Bank as one of my primary research facilities for many years. Done some projects here, including a large project we may touch on later. So I'm familiar with the observatory. I've been a visitor here many times, given a few talks here, attended a few workshops. And so when this opportunity became available, I said, that looks like a good job for me, and I'm delighted that they chose me. It's been fantastic.
Now, part of your own work involves studying the molecular clouds of the galaxy and probing that. Now, this sort of a thing goes back a long way. As I recall, the infamous Big Ear telescope at Ohio State was originally designed to map hydrogen clouds in the galaxy. Correct. And was obviously then repurposed for SETI purposes. But originally, it was surveying hydrogen. Now, before we get to more complex stuff,
sure,
what handle do we have on the hydrogen clouds of the galaxy since then, since we've studied them so long?
Yeah, it's a great question. This is one of the rare instances in astronomy where a prediction led the observations. It's usually the other way around. Back in the late 40s or early 50s, the prediction was that atomic hydrogen, neutral atomic hydrogen, should be emitting a spectral line at radio wavelengths, 21 centimeters. And that people went and looked for it, and they found it. It turned out to be true. And ever since then, this 21 centimeter radio line of hydrogen has been a way that astronomers can deduce the hydrogen content of the universe, map these hydrogen clouds. And there was quite a cottage industry that has done this. And we still do that to this day with essentially every radio telescope does some atomic hydrogen. So, we can map these clouds. They're throughout the Milky Way. They're ubiquitous, and we can see them in other galaxies as well. So these are kind of diffuse gas clouds. Typical density you can think of 1 particle per cubic centimeter. So 1 hydrogen atom every cubic centimeter, which is very, very diffuse gas. Much, much better than any laboratory vacuum you can make. And so that's kind of spurred the game to realize that there was gas and dust between the stars. So this is kind of a big impetus for radio astronomy, is studying this line and the structure of the galaxy and the structure of these clouds.
When these clouds get dense, you get star-forming regions. Now, what causes let's say the early universe, as best as we understand it, in the early universe with these hydrogen clouds, this diffuseness, what causes the clumping that eventually leads to stars?
So early universe is still pretty mysterious. We don't really have a good handle on how the first stars form, but let's move on to, say, I don't know, redshifts of 10 or so. Still very early in the universe, but not like when things were hot. And the universe had to cool off enough so that the atoms the electrons and the protons could combine into atoms and stay there. So once gas clouds formed, probably the galaxies formed first, and the gas clouds came along for the ride. And then once you have the gas kind of trapped in the gravitational potential well of a galaxy, they'll start to condense under their own weight. It's basically gravity will always try to pull things together into smaller and smaller pieces until something pushes back. So in diffuse gas, there's not a lot of pressure, there's not a lot of pushback. And so the clouds will naturally kind of just condense and form denser structures. And eventually, once they get dense enough, then the atomic hydrogen will start to convert itself into molecular hydrogen. And those are the clouds that I study.
Now, molecular hydrogen is infamous for the hydrogen line, 1420 megahertz or thereabouts, shifting all around as the clouds move. And that's supposed to be a protected spectrum for radio astronomy, right? It has been since the 70s. Do you still get interference, even though it's supposed to be?
Okay. So a couple points. First of all, the molecular hydrogen is not the 21 centimeter line. That's atomic hydrogen. So that's hydrogen atoms only, and they haven't combined into hydrogen molecules. So yes, that line is at 1420 megahertz, and it is protected. Now, I will say it's still pretty clear. So there's an international treaty, international laws that prohibit broadcasts in those frequencies. And yet, we are seeing more and more that there is some interference that we see in these protected bands. And not all radio bands are as protected as this particular line, but this particular line should be absolutely quiet. And the point is, though, our receivers are becoming so sensitive now that things that we wouldn't have noticed even 10, 20 years ago, we are seeing signs of now. A lot of this emission is not intentional. There might be like harmonics of a transmitter at a lower frequency that is just not particularly well designed, and so you still have some power being emitted in these protected bands. So, and some of it is broadband. So if you have, a lightning storm, you'll see emission in this protected band. It's not human emission, but it is a source of interference for us. So, but by and large, these bands are still fairly well protected. They're still quiet. Now, Green Bank sits in another particularly interesting place where we have an extra level of protection here in the radio quiet zone, which is a zone of limited radio transmission. And there's another special zone right around Green Bank itself. It's a West Virginia radio astronomy zone where within 10 miles of the observatory, there are even more stringent requirements for radio transmissions.
Now, how bad is lightning as far as a broadband signal? Because anybody that's ever messed with an AM radio during a thunderstorm knows, knows what lightning can do.
Lightning's pretty bad. It's hard to observe during lightning storms. I mean, you can when the lightning will generate a radio pulse, and you just have to flag it out of your data. So it's an irritant. Luckily, it doesn't happen very often. What's affecting us more, and not at the 21 centimeter line, but in general, we're getting more and more sources of interference like Wi-Fi, 5G transmitters, like DirecTV, satellite television transmitters. They're transmitting radio waves, and then we can easily see their signals, and that interferes with astronomical signals. So there are some bands that we're just going to lose. I mean, I don't see much hope of combating technology to the point where we say that's it, we're going to ban DirecTV forever. That's not a practical solution. But we are working with some of these satellite companies like SpaceX to see if we can find a way to share the spectrum gracefully and maybe share it in terms of time. Like, for instance, if they have the choice of broadcasting at two frequencies, they'll broadcast at frequency 1 for half an hour, for the first half hour of every hour, and frequency 2 for the second half hour of every hour. And then we can observe in the quiet band and then switch to the other band when that's not being broadcast in. So there are some solutions, or we can ask them, please, pretty please don't broadcast when you're over the radio telescopes. It's a fact of life, though, and there are even sources of radio emission, like, they're going to require radar detectors on it, not detectors, but radar systems on every car, right? So that you avoid collisions. Well, those are radio transmitters, right? Many cars have Wi-Fi signals, Wi-Fi capability. And so the more transmissions there are, and the more technology there is, the more demand there's going to be for the precious spectrum. And the astronomers have to work with our partners in industry to make sure that we can still do our jobs and satisfy their needs as well.
What do you think of the idea that's being floated of perhaps putting a radio telescope on the far side of the moon?
That would be fantastic. That would avoid a lot of the problems until the moon becomes so populated that it too has its own FM stations. But I think in the interim, that it's actually a good solution. It's expensive, of course, to lift things to the moon, and it would be hard to at our current stage of technology to launch something like the Green Bank telescope or construct something as big as the Green Bank telescope on the moon. But if you're talking about simple systems where you just kind of lay wires out, or dipole antennas, which are basically just stretches of wire, yeah, that would work very well, and it would work beautifully because the moon would block the signals from the Earth, and there's no other source of radio interference.
I think it's very poignant that we talk about our level of technology, given that James Webb deployed its secondary mirror today and seems to have done it flawlessly. So yes. we seem to be stepping up in capability of deploying space telescopes, and yes. I think the next logical move might be a radio telescope.
Yeah, sure. There have been orbiting radio telescopes before. The Radio Astron project have deployed a little radio antenna and used it for long baseline interferometry, VLBI technique. So yeah, it's not a crazy idea to think about deploying radio antennas into space or into the far side of the moon. Astronomy has always been kind of leading technology and cutting edge technology. We're pushing the envelope to get more and more sensitive receivers at more and more wavelengths to see what's out there. And some of these technological developments are amazing. And I'm delighted that JWST went off without a hitch. And that's a real tribute to that team and the years of effort and sweat that went into that project.
Yeah, and just to watch it just go so well. What was it, something like 370 single point failure possibilities, and everything went just perfectly. But that's been the track record. I mean, I think the most recent Mars rover had 100, and everything went perfectly and did it very rapidly in a very set schedule, or it would have crashed. Yeah,
as we push the technology, right, we're always on the cutting edge, but we learn our lessons, and the next missions go off with the benefit of the lessons learned from the previous one.
Now, back to star formation and what eventually happens. So you get the first generation of stars, which we don't really understand all that well, but James Webb may help us with that. Now, then we get to some supernovas, some explosions, and we get the heavier elements. And that we understand quite a bit better, and that also plays into the population of the clouds of the galaxy, right?
Mm-hmm. Yeah. So look, it's a very interesting cycle, and what we can get back to the early phases. But let's say we're in a galaxy like the Milky Way, where you've been around for several billion years, and it's kind of a steady state system. There's an ecosystem, And as you say, supernovas play a role in it, and that's how we seed the gas in the galaxy with these heavy elements. So as the heavy elements, heavier than, say, carbon or oxygen, are all formed inside of supernova, massive stars that explode as supernova and spray those elements out into space. Now, so for some elements like carbon, they can also come out in like evolved stars, like asymptotic giant branch stars, where they're formed they're dredged up from the core and they're part of the envelope, and then they'll spray out into space as the stars puff out as planetary nebulae. So there are other ways to inject these atoms into space. But all heavy atoms, heavier than hydrogen and helium, which were formed in the Big Bang, were formed inside of stars. And then the consequent evolutionary system, ecological system of star formation enriches the gas with these heavy elements. And then as time goes on, the gas becomes richer and richer in these heavier elements until you reach the state that we're in now. And now we have carbon and nitrogen and oxygen as kind of not particularly common constituents, but normal constituents of molecular clouds. And so when a new star forms, that gas already has these heavy elements in it, and you can start to generate some really interesting chemistry. You can generate dust grains, which makes the clouds dark and helps to shield them from the light, the ultraviolet radiation in space. And so the cycle of star formation seeds the next generation, and then we can start again. When you make these molecular clouds, now they're dark and protected. They can condense, they make a new generation of stars, and on we go. So it's a really interesting interplay between what happens in these cold, dense clouds and then what happens as these stars explode and fill the rarefied gas in the Milky Way with their ejecta. We have a personal interest in this because we're made out of this stuff, right? So every carbon in your body was inside of a star. Every oxygen atom in your body was inside of a star. And by the grace of supernova, they become part of planets, and they become part of Earth, and they become part of us. So we owe our existence to the star formation process and the star formation ecosystem.
That's an interesting thought. All life in the universe owes its genesis ultimately to supernovas. And as a result, when you look at these clouds, you see some very complex molecules as well. Mm-hmm. We started with hydrogen, but let's get into aromatics, where you get these much, much more complicated molecules that begin to start looking like the stuff that becomes life.
So it's an interesting and fascinating story, and that's just one of the things that actually got me interested in this field. Right around the time I was a graduate student, they were beginning to discover molecules in space. My graduate school advisor was the first person to find OH, the hydroxyl ion, in space. And as time went on, more and more complex molecules were discovered. It was originally thought that space was too harsh to allow these molecules to either form, or once they form, to stay in molecular form. They stay as molecules, to stay bound together. So as we make more and more complex molecules, then we start to see more and more chemical reactions as these molecules bump into each other. Now, again, it's pretty diffuse stuff. Chemistry in space is a bit different than chemistry in a test tube. But you can imagine very rarely carbon monoxide molecule that forms in space will bump into a water molecule and form some interesting combination from that collision. And as time goes on, you make more and more complex molecules. Now, the aromatics you're talking about are a fairly recent phenomenon, fairly recent discovery. They were first hinted at in I would say, the 70s, were these infrared bands that no one could really quite identify. And then it was realized that you can think of them as either very large molecules or very small dust grains. Right, so they have ring-like structures in them, and as the rings kind of connect together, you make structures of multi-ring structures that can be more and more complex. A good example of these polycyclic aromatic hydrocarbons are the char on your steak. I like a good char on my steak, and the molecules in that char are these things. These are these complex ring molecules that add some flavor and aroma, and so the rings add the aroma. Your nose is sensitive to these shapes. And we find these now in space, and we're beginning to identify, for the first time, we're beginning to identify which of the thousands of polycyclic aromatic hydrocarbons can be out there are actually out there. There are dozens and dozens and dozens of combinations of these rings, and we know, in general, we know that there's some hydrogen atoms sticking to these rings, and they will form a particular type of infrared feature that we see in space. But finding out exactly which ones are out there, or which class of them are out there, has been pretty difficult, because it's hard to distinguish something with 20 rings from something with 19 rings, say. So that's a subject of active research, but it is fascinating. And of course, life has ring molecules in it, and the DNA molecules have these kind of ring structures in them. So these, I'm not saying that life originated in these molecular clouds, but the basic elements necessary, the basic compounds necessary for life, may well have originated in space and been transported to the early Earth.
And it's interesting to note, as I recall, this is all corroborated by meteorite evidence with the carbonaceous chondrites, where they've actually found some of those chemicals in there, but also amino acids, which,
That's right.
It could be this,
Yeah.
You're getting
And
into
again, no one's
building blocks.
suggesting that amino acids formed directly on the meteor, right? But they form naturally in space and become part of material around the forming sun that then becomes part of meteors and are delivered to Earth.
It's absolutely fascinating that this process that can lead to a planet like Earth, it so much has to go a certain way within the universe before you even get to the complexity needed to for obviously complex organic chemistry like DNA or something like that, which we still don't really know how that happens.
Exactly.
Now, one point I want to make is that radio astronomy, and you made this point in another interview, radio astronomy is accidental and really only begins in the 1920s. Could you give us an overview of the accidental discovery of radio astronomy?
Yeah, so look, the first real radio, the first inkling that radio waves were emitted from celestial objects was Karl Jansky. He was working for the Bell Labs. He was working for the phone company. And the phone company in the 20s had this radical idea that they might want to transmit voice signals over radio, and maybe even tower to tower, or maybe eventually, maybe even with satellite. Now, satellites were not around then, but it was definitely they were thinking about radio telephony. So, in order to understand the viability of that approach, Jansky was tasked with okay, well, what's the sources of radio noise, radio static, that might prevent or might hinder the clear transmission of voice signals? And so he built this amazing contraption. It looks like a fantasy merry-go-round with no seats. It's a thing that sits on a big round track with a bunch of dipole antennas, wires that are strung out on this kind of wooden frame that he made with 2x4s. I think he used Model A parts for his wheels and for his engine. And then he would just move this whole contraption around. So it had sensitivity in a particular direction. And then he would rotate it around to try to locate the signals. And what Jansky found was he found three sources of radio noise. One was nearby lightning, which we've already talked about. One was actually distant lightning. And this was a surprise, and they didn't quite understand how radio waves propagated in the Earth's atmosphere. It was probably radio waves from lightning storms that were reflected off the ionosphere and then back to the ground. And then there was another source of radio noise or static, which was actually what we would call a signal now, that seemed to change its direction. It wasn't at the same place in the Earth's atmosphere every day. It would change, and it would move across the sky at the same rate as celestial objects move, during the course of the year. So as the Earth orbits the sun, right, you get a different view, and Orion is up above, Orion's in the nighttime in winter, but it's in the daytime in the summer. And what he found was that this source of radio static moved at the sidereal rate rather than the diurnal rate, which means that it followed the stars on the sky rather than the sun, right? So it was clearly something in the sky. It turned out what he'd found was the center of the Milky Way, which is a very bright emitter of radio waves. He was finding synchrotron emission from the center of our galaxy in the galactic plane. And that was an amazing discovery. So that's kind of the origins of radio astronomy. And the building here is called the Jansky Lab, and the unit of radio flux is called the Jansky. So he was famous for that. Oddly enough, he never really followed up on it. I guess the telephone company thought it was a nice, interesting PR result, but it wasn't really helping them with their telephone business. And so that's kind of his first and last brush with radio astronomy. And it kind of sat dormant for many years before astronomers picked up on it again. And it was amateur astronomers actually who picked up on it again and got the momentum going to make it a serious kind of mainstream astronomy technique.
And now we've learned just so much from it over just the last few decades, really, with radio astronomy, that it's now an integral, extremely important area of the spectrum for studying the universe. Now, to touch back onto star formation and your work,
sure,
and how stars, as they form, disrupt their environment.
Yeah.
And that begs a question. So, is there a moment when a star actually touches off and sparks up, or is it a long, slow process of a little bit of fusion going and then bigger and more accreting and things like that? What does that look like?
Yeah, no, that's a really interesting question. So it does go through stages, and we can say on astronomical timescales, star formation happens fairly quickly. On human timescales, it takes a while. But let's say these clouds, these molecular clouds are collapsing and condensing and fragmenting. And when these fragments get to stellar mass sizes, say 10 or 20 or 30 solar masses, they will begin to collapse under their own weight. So the idea is there's a fight between the pressure pushing out, due to the gas pressure, and the gravity pulling in. And there's a certain mass over which that threshold is reached where gravity has to win. So if the mass exceeds a certain amount of mass called the Jeans mass, gravity wins, the thing collapses. So imagine you have this first it's very cold. It's just this cold molecular gas, 10 Kelvin, 10 degrees above absolute, just slightly warmer than the microwave background. And then as these clumps collapse, they get warmer and warmer and warmer due to essentially the energy of falling down down the potential well of the gravity. And it warms up and forms what's called a protostar. Now, a protostar is not shining by itself like the sun is by nuclear fusion reactions, because it hasn't reached a point where it's hot enough in the center or dense enough in the center for that to happen. So the star will be going along in its protostellar phase, and it'll reach something like, room temperature, toasty by interstellar standards, but it's still very cold compared with real stars. And then there's a point at which the center of the star will continue to get hotter and denser, and eventually it gets hot enough and dense enough where nuclear fusion reactions can happen. Now that's very hot and that's very dense, but as this process goes along, it just continues to get hotter and denser. And once that happens, I think that's the point at which I would call it a star, once it's generating its own internal energy through fusion reactions. Now that's of course not the end of the story. Once that happens, the star will continue to grow and accumulate mass from its surroundings as stuff falls down onto the star. And it's not entirely clear what the exact path is, but most people think like a high mass star that's much more massive than the sun will enter the hydrogen burning phase, or the real stellar phase, but continue to grow and become just brighter and brighter and brighter until it runs out of material that falls down on it. And then it's done, right? Now, all along the way here, the star will continue to affect its surroundings. Now, it'll generate, even these protostars will generate some energy, right? They're glowing in the infrared, and they're generating heat, and they're putting energy in. So it starts to heat up a little region around the star. But once you get these stars, these big stars especially, they're going to start putting out a lot of energy in the form of radiation. They're going to have winds like the solar wind, but more so. And that stuff will start to push on the material around it. And if the star is really hot enough, it'll ionize the gas around it. And then you'll start to make these beautiful bubbles. I don't know if you've seen these images of H2 regions, they're called ionized hydrogen regions. Orion is a good example, where the stars are so hot that they're beginning to ionize the gas around it. And this is the beginning of the story, where we're starting to push material back rather than pull material in. And eventually, if the star is massive enough, it'll explode. And then we're back at the end of the cycle, and we'll condense that enriched material into a new star. So it's a really beautiful and interesting cyclical process.
Now, we are, as we hinted on earlier, a supernova remnant, essentially. Our solar system formed out of that. So some giant star, some precursor explodes, and the solar system condenses and forms out of it. Now, what do we know about that supernova that created the protoplanetary disk of that the solar system formed?
Well, that's a bit of a misunderstanding. So the protoplanetary disk didn't form from a supernova explosion. I think it's safer to say there was a supernova explosion in the vicinity of the sun, and that material, we are enriched with that material from that supernova. And the reason we know about it is there's supernova, when they explode, put out a whole bunch of heavy elements, and some of those elements are stable and some of those elements are unstable. So what we're talking about here is an unstable element of aluminum, an unstable isotope that's still radioactive. Now, if it had happened billions and billions of years ago, all that radioactive aluminum would have decayed into its daughter products and would be gone. So the fact that we're still seeing it means that the supernova happened within the half-life, roughly, or one or two half-lives of the aluminum ion, or the aluminum isotope. So we know that the supernova was not at the beginning of the universe, but maybe within a billion years or so of this formation of the sun. Now the supernova itself doesn't cause this protoplanetary disk, but it can affect its composition, put it that way. Some of the spray from the supernova can get into the stuff that later becomes the disk. The disk actually forms from just the gas. As the star condenses, there's a little rotation, and when rotating things collapse, they start spinning faster and faster, like the ice skater. At the end of every ice skating competition you've ever seen, the figure skater will begin a spin and then pull in his or her arms, and they'll spin faster and faster. That's what forms the disk. It's that rotation that causes a centrifugal force that collapses things into a disk. And this solar system kind of remembers the sense of that rotation, right? Because all the planets orbit in the same direction. So that's the sense of rotation of that orbiting disk.
That brings us, the idea of rotating and ice skating brings up another thing that you guys do at Green Bank, and that is probing gravitational waves with pulsars. Could you give us an overview of that research?
That's really fascinating stuff. And I'm really, really happy that Green Bank is doing this work. It's really kind of interesting. So, look, one of the predictions of Einstein's theory of relativity is that you can't think of gravity as a force of something over there immediately acting on something over here. What Einstein's conception of was that you have to think of space and time kind of woven together as this fabric. And that gravity is the curving of that fabric by the presence of a gravitational mass, right? So you have a mass like the sun, the fabric of space and time around it is slightly bent. And what that means is that light, which follows straight lines, will actually follow slightly curved lines. And you can think of gravity as the Earth kind of falling around the sun, but the material or the substrate that it's falling around is actually bent. And so it's not following a straight line, it's following a curved line because the space and time around it are actually curved. So back to the pulsars. So imagine that we have two really massive things kind of coalescing. What that will do is then send out ripples of space and time, gravity waves. And what that means is that distances are kind of oscillating around and time is kind of oscillating around. So the distance between things will get longer and shorter slightly. And the length of times that clocks measure will get longer and shorter slightly. So what we have finally detected gravity waves with the LIGO experiment, and this is measuring the distance fluctuations, right? So LIGO are these underground chambers where you have mirrors. You measure the distance to the mirror with a laser interferometer, and you actually see as a gravity wave passes, the distance changes. Now, it's a very subtle effect. You're looking at very tiny changes over several miles. But they've seen these effects by using lasers as their ruler. What we're looking for with Green Bank is not a change in distance, but a change in time as a gravity wave passes. And so, how are we going to measure that? So we're going to use the best clocks we know, and these are the pulsars. Pulsars are the end states of stars, rotating neutron stars. So at the end stage of a star that's, say, like the sun or bigger, slightly bigger than the sun, maybe solar mass, the end state of that is going to be maybe a neutron star, maybe think of a slightly more massive star than the sun. What happens in that condensed object, so all the material from that stellar core is condensed into a matter that's so tightly compacted together that there are no longer atoms and nuclei. It's like a giant massive neutron. So imagine you took the sun and put it in a big trash compactor and squeezed it down to the size of Manhattan. That's a neutron star, right? So it is extraordinarily dense, like a cubic centimeter of, like a sugar cube worth of neutron star material weighs about as much as all people on Earth, right? Now these neutron stars will rotate, and as they rotate, they have very strong magnetic fields that if you're looking down the throat of that magnetic field, you'll see a radio pulse. And so if they rotate around, sometimes that the magnetic field will be pointing at you. Most of the time it will be pointing away from you. So you'll see a pulse, and then nothing, a pulse, and then nothing, a pulse, and then nothing, just like a lighthouse. Now they rotate at extraordinarily fast speed, many of them. So think of taking the sun, compacting it down to the size of Manhattan, and then whirling it about as fast as a blender. That's a nice model of a neutron star, right? And so as this thing spins around, because think of a really good top that has no friction. It'll just keep rotating and rotating and rotating, and therefore those pulses are going to be emitted very regularly, and you're going to see them at very regular periods. They're perfect clocks, in other words. So these pulsars we're using as clocks, and as a gravity wave passes, in some directions you're going to see the clocks slow down. In opposite directions, you're going to see the clocks speed up. And so what Green Bank does is we look at a bunch of pulsars all the time, and we measure their rates. So we measure the clock speed, if you will. And if you look at enough of them long enough, you might notice that, gosh, for a couple weeks, all the clocks in this direction were running a little fast, and all the clocks in that direction were running a little slow. That would be the signal of the passage of a low frequency gravity wave. And that's the point of this experiment. Now, these low frequency gravity waves are not generated by kind of stellar mass objects coalescing, which is what LIGO might measure. But these are much bigger things coalescing, like millions and billions of solar mass black holes in the centers of a galaxy coalescing would emit these very low frequency gravity waves. So, we've been on the lookout for these by timing pulsars with Green Bank. The project keeps going. Stay tuned for the result. If they see a signal, it'll be a fantastic result for the observatory.
That's interesting because it would also be a probe completely separate from LIGO, of
Correct.
this phenomenon. So we would
And a
have
different,
two ways.
it's yes, exactly. It's in a different kind of regime of black hole physics, not the tiny little ones that are like stellar mass or neutron star mass, but giant ones. It'd be absolutely fabulous.
Now, the future for Green Bank, I had heard that given the collapse, the tragic collapse of the Arecibo radio telescope, that telescope had, I assume, one of the most powerful transmitters on Earth so that it could do radar work and map asteroids and the moon and things like that. Now, I had heard that capability is coming to Green Bank. Could you give us an overview of that?
Yeah. So look, no astronomer on Earth was happy to see the unfortunate demise of Arecibo. That was a very sad day for astronomy. But it does leave a gap in our capability. And as you say, radar was one of those gaps. We are exploring the idea of developing a high-powered transmitter for Green Bank. Now, Arecibo was a bigger telescope, much bigger telescope than Green Bank, believe it or not. But Arecibo is 300 meters in diameter. Green Bank's 100 meters in diameter, so it had about 9 times the collecting area. What Green Bank can do, though, that Arecibo couldn't, is point all over the sky. So we're fully steerable. We can point in any direction. And Arecibo had a limited range over which it could point. It had to wait for things to pass overhead, essentially. We think we can fill this niche pretty well by adding a radar transmitter to Green Bank. Now, look, we've done a little work with radars at Green Bank before. Not nearly as powerful as the Arecibo transmitter, but we're confident we can do that, and we think this will be actually a nice opportunity for us to do some interesting science and to do some different science for us. As you say, what you can do is measure the surfaces of asteroids. You can measure the rotation rates of planets. You can study the surface composition of moons and planets, and satellites. So it's actually a very interesting opportunity for us. And we have some study money now to develop design for such a transmitter. And I hope that design goes well, and I'm pretty confident that, if we talk again next decade, we'll have a transmitter system on Green Bank, and we'll be doing some really interesting work in planetary radar.
Now, will it be comparable in transmission power to the one that was at Arecibo? Because I remember that one was powerful enough to sort of create a token signal and send it off towards a star cluster as the Arecibo message.
If we wanted to get the attention of our neighbors, Arecibo would have been a good way to do it. It won't be as powerful as Arecibo, but it will be pretty close. We're looking at something like a 0.5 megawatt transmitter, maybe 0.75 megawatt transmitter. So it would be a powerful system. Now, the nice thing is if you combine this with lots of collecting area, say with the new radio telescopes that are being envisioned, like the next generation VLA, that combination of the Green Bank as a transmitter and all this collecting area with the new radio telescopes would make it a much more powerful system than the Arecibo system alone.
Now, what about FAST? Now, that's sort of comparable, of course, a little bit bigger than Arecibo, but works very similarly. Does that have transmission capability?
Yeah, FAST is a very impressive instrument. Now, it has a larger diameter than Arecibo, but it has about the same useful collecting area. It can look at things as they go further over than Arecibo did. Even though it has a bigger surface, it can't use all that surface at once. So it's similar to Arecibo's collecting area, but it can look at more of the sky. FAST is great, and for if you what you need is raw sensitivity, FAST is quite a powerful instrument, and would be superior to Green Bank. Green Bank does have the advantage that you can look all over the sky. So Green Bank also does a little bit better at higher frequencies than they do. So we're not competing head to head with FAST. We just do different sorts of science. We play to our strengths.
Now, when you do get to these transmissions and start mapping asteroids, is that basically the only signal that we produce that, say, within 100 light years, an alien civilization could catch and say, well, that's our wow signal, or something like that? Do you think that it's that powerful, or do you think that it's just too transient and they probably wouldn't notice it even if it was there?
Boy, that's a great question. So one of the teams that works with Green Bank are the Breakthrough Listen colleagues, and they're doing kind of the search that you're suggesting they're looking for technosignatures, right? And one of the rationale behind this is radio waves are easy to generate. They don't cost a lot of power. If you make a very narrow band signal, it would stand out from cosmic sources of radio waves and would be noticeable, right? And so the idea is that radio waves may be a very interesting way or a common way for civilizations to communicate or to announce their presence or to advertise their presence. And we are inadvertently advertising our presence by the radiation that's leaking away from the Earth every day, television and radio signals that make it through the ionosphere and out into space. And a radar system like Arecibo is a very tightly focused beam in a particular direction. So if you wanted to blast a radar signal at some of the nearest stars, and that would be a good way to announce that we have technology. Then the question is, are the other planets, do they have life? Do they have intelligent life with technology? Do they use radio waves to signal, and are they trying to announce their presence to us? And it's a very interesting question. The famous Drake equation, which estimates the number of communicating civilizations, was made over here in the Green Bank Lounge over some glasses of wine. Estimates the number of such civilizations depends on many factors, and we just don't know the number of all those factors. But we're beginning to chip away at some of them. We know that most stars have planets. The real question is, how many planets have life? And of that, how many have intelligent life? And of that, how many have technological capabilities and are trying to communicate? And then, of course, the scary number in the Drake equation, or the scary factor, is once you develop technology, how long does your civilization last? Because if you blow yourself up immediately after developing radio technology, there are not going to be many communicating civilizations out there. I asked these guys the question, so how far could you see Earth? And their answer was about 10 light years. With Arecibo, they said you could increase that, or with a radar system like Arecibo, you would increase that probably to 100 light years. So we haven't been spending all of our time beaming, radar signals at the nearest stars. Could, if we wanted to devote the energy and the time to it. But inadvertent kind of leakage radiation, if there was a civilization within about 10 light years with radio telescopes, they would notice something funny is going on with Earth.
It's interesting, though, because Earth itself is an exoplanet. It has been broadcasting its weird oxygen levels and methane levels and things like that for far longer. So the entire galaxy may know that there is an exoplanet here with the biosphere, but all of a sudden, then they see a radio signal, and they're like, oh, they've hit
That's
it.
right.
Or it's a sad situation where nobody's radio in the galaxy is powerful enough to make it to anyone else, and you just can't, nobody can pick each other up.
Yeah. Or, they developed another form of communication. Maybe they, communicate with, neutrino waves. Who knows, right? And so we're very early in this technology game. And, we're assuming that they're like us. That's always been a fallacy when we think that we're something special, right? Or when we think we're someplace special. So, to be continued, but the technosignatures is the one thing that, this type of work that we do here, where we're looking for these radio signals. Another approach, as you said, was to look for, biological signatures, like, free oxygen in the atmosphere, or, phosphine or something like that, which if life is like ours and based on the same principles as ours and developed along the same line of ours, some molecules can only exist by constant replenishment by life. And so that's another interesting avenue. And we're just entering the phase of technology where we may be able to start seeing these things. So I think that if there are Earth-like planets out there with oxygen and methane and phosphine in their atmospheres, we may get that news within the next decade. We just starting to reach the sensitivity where we can detect those signals.
And James Webb, that space telescope, it begins that process. And then imagine what we're going to know within 100 years. Considering when I first became an amateur astronomer, we had never actually confirmed an exoplanet back in the 90s. And all of us, now we have thousands. thousands of these things, and they're ubiquitous. There are more planets than there are stars. So it was amazing to watch it unfold. And I wish you great luck at Green Bank, and check in with us again sometime. And it was a pleasure having you, Doctor.
Oh, thank you so much. I really appreciate it. It was fun chatting with you. We'll do it again.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?